All right, gas stoichiometry. This video is going to be on how we solve stoichiometry problems using gas laws. So reactions happen in moles. So we're going to have to convert whatever you're given to us or whatever we're looking for into obviously into moles. We are adding new tools to our tool chest when we convert to moles. The first one is if it's a gas at standard temperature and pressure, STP, which means it's at 0 degrees Celsius and 1 atm. 1 mole of gas occupies 22.4 liters. So that's a very important, nice little relationship there if we're at STP. So 1 mole equals 22.4 liters is a real nice relationship if we're at standard temperature and pressure. If we're not at STP, then we'll have to use the ideal gas law, PV equals nRT, to calculate whatever it is that they want to calculate. So we're kind of adding two tools to our stoichiometry tool chest. 1 mole equals 22.4 liters at STP, or PV equals nRT when it's not at standard temperature and pressure. So we're just going to do two examples, one at STP and one that's not at STP. Okay, so example number one, mercury can be achieved by the following reaction. So mercury oxide is heated and it decomposes into liquid mercury and O2 gas. And the question is asking is what volume of oxygen gas can be produced from 4.10 grams of mercury 2 oxide at STP? Okay, step one is to make sure I'm balanced. So I have two oxygens on the right, I gotta have two on the left. And that means I gotta have two mercuries, so that is now balanced. Step two is what is given to me, and what am I looking for? So what is given to me is 4.10 grams of mercury oxide. So I'm gonna put 4.10 grams right here. And I'm looking for what volume of gas, of O2 gas, since O2 is the only gas in this problem. We can only apply gas stoichiometry tools with gases. Okay, next step is we gotta convert our given into moles. Oops. So I have 4.10 grams of HGO, and I can convert that to moles. So that means I gotta divide by the molar mass. I have to add up one mercury and one oxygen on the periodic table, and I get it to be 216.59 of HGO. And that's equivalent to 1 mole. So that's my molar mass. Okay, now I gotta do the mole-to-mole ratio, since I've now converted to moles. The ratio is a 1 to 2 ratio, so it's a 1 there and a 2 there. So for every 1 mole of O2, it's going to be 2 moles of HGO. Again, my units are canceling out as I'm going across my dimensional analysis. Since I am at STP, I'm going to use this nice relationship. 1 mole of any gas is equal to 22.4 liters. And I'm going to use it right here in the end. For every 1 mole of O2 gas, it's going to be equivalent to 22.4 liters of O2 gas. Okay, so my setup is correct. All my units will cancel out. Grams of HGO, grams of HGO, moles of HGO, moles of HGO, moles of O2, moles of O2. All my numbers are correct. I'm just going to do the math. Now, 4.10 times 1 times 1 times 22.4, divide by 216.59, divide by 2, plug it in the calculator, and I get an answer to be 0.212 liters. Okay, so again, what's nice about questions that are at STP is we can use this nice little relationship right here, that the relationship between moles and volume right away, but it has to be at STP. Okay, next question. Okay, so what happens if it's not at STP? So I have the same question, but my conditions are not at STP, so I have it at 400 degrees Celsius, and I have 0.974 atm. I'm still using the same problem as before, so I have 1.4 grams. I still have to balance from the previous question. Okay, and I'm still looking for the volume here. So, all right. in order to use the ideal gas law, so I'm gonna have to use this formula now, PV equals nRT, and I'm gonna be looking for the volume of O2 there in this expression. So that means I'm gonna divide both sides by P, and eventually I'm gonna have to find the moles of O2, the gas constant, the temperature, but it has to be in Kelvin, and my pressure has to be in ATM. My pressure is already at ATM, so I gotta convert my temperature to Kelvin. So that is now 673 Kelvin at this point. Okay, so my temperature's in Kelvin, my pressure's in ATM, so that's good. So now I'm going to start my stoich. I still have 1.0 grams of HGO. Convert that to moles of HGO. So for every 1 mole of HGO, and again, the molar mass is 216.59. Okay, now the next part is I'm just only going to go to the molar ratio. So for every 1 mole of O2, that's going to be 2 moles of HGO. And the reason why I'm only going to the mole-to-mole ratio is because this will give me my moles of O2, which I need for the ideal gas law. So I don't have to go beyond that. I'm now going to plug in this in my calculator, and I'm going to get an answer to be 9.9265 times 10 to the minus 3 moles of O2. Okay, so now that I have my moles of O2, I now have my N over here. I have R, I have temperature, which is at 673 Kelvin, and I have pressure. So now I'm going to use this expression, volume equals nRT over P. My moles is 9.9265 times 10 to the minus 3. My R is a gas constant, 0.0821. And my temperature is in Kelvin, which is 673 Kelvin. Divide this whole thing by the pressure, which is 0.974, and plug this in my calculator, 9.9265 times 10 to the minus 3 times 0.0821 times 673 divided by 0.974, and we'll get an answer to be 0.563 liters. All right, so we worked out example number 1 is at STP, and example number 2 is non-STP. We're just adding more tools in terms of how to solve gas stoichiometry questions.